So thank you everyone for coming to our Innovative Discovery series. We are very excited today to have our own Paul Kolm to give us a talk on use and misuse of statistics in medical research. That's going to be great. So before I introduce him, let me mention some housekeeping issues. First, please make sure that you sign in. The sign-in sheet is just right there on the table. Please RSVP so that we can better prepare for the next session. Online participants, please keep the mics muted unless asking a question and keep the video turned off. Use the chat feature in BlueJeans if you have technical questions. The next in our Innovative Discovery series will be presented by Dr. Yukiko Washio on March 11th. And it will be maternal and infant behavioral health and nutrition. And then we will have moving community engaged research from participatory toward anticipatory by Brian Reimer on March 18th. We are starting a new series which is called Tech Talk, and that will be monthly on Thursdays. We'll start on April 7th. That will be the first Thursday of the month. And it will be a seminar focusing on technical aspects of statistics, epidemiology, bioinformatics methods, and how they can be applied to medical research studies. So we have flyers in the back. Please grab the flyer to learn more. The full schedule of the Innovative Discovery series and the Tech Talk is on the website. And all the previous presentations are also available on our website, DE-CTR. So I'd like to go back to Paul, and I'm so happy and very happy to introduce him. So Paul is currently a professor of medicine at Thomas Jefferson Medical College in Philadelphia, and also the Director of Biostatistics at Christiana Care. He has a PhD in psychology and measurements from University of Nebraska-Lincoln, and from there I've had a very distinguished academic career. He started his career as assistant professor in statistics at Southern Illinois University in Medicine in Springfield, then worked as a director of biostatistics in the Eastern Virginia Medical School in Norfolk in Virginia, and then the director of research at the Naval Medical Center in Portsmouth, Virginia. Then he moved in 2002 to Atlanta, where he was associate professor of medicine at Emory University School of Medicine, and Director of Biostatistics at the Emory Center for Outcomes Research, where we both worked, which was led by Dr. Weintraub in the cardiology division at Emory. He has taught multiple courses in biostatistics from the basic level to very advanced level, and the first Tech Talk will be a pause, actually, we will talk about time series. He has a very long list of publications, has been funded as a co-investigator biostatistician on multiple grants, and has been instrumental in the success of many of our own grants. So thank you so much, Paul, and we look forward to talking.
I'm kind of really nervous about this. I think I'll either enlighten everybody, or I may have to resign. But anyway, as I put this together, actually, I kept coming up with more and more topics to talk about, and realized that there's no way I'm going to fit them all in an hour. So I'm not even sure I'm going to be able to get through what I have. So we'll sort of see how it goes. But I wanted to start out talking about myself. And I have a reason for this, but I've spent 6 years total on IRBs in 2 different institutions. I was 3 years on an IACUC, that's the Institutional Animal Care and Use Committee. That's basically the IRB for animal research. I've been on a number of DSMBs, at least 3. I'm probably more, but I couldn't remember all of them. I've been a statistical reviewer for a number of journals, some statistical journals and then clinical journals. When I was at Emory, I was a member of the GCRC advisory committee. That wasn't the IRB, but it reviewed the protocols for scientific merit. So I did that for several years. I've been a member of the American Heart Association Clinical Outcome Study section. I found out this year that you can only be on it for 4 years consecutively, and then you have to sit out a year before you get back on. So that's why I was there. There's another study section I've been on, but I couldn't remember that one either. And currently I'm the statistical editor of the Journal of American Cardiology Interventions. Apparently, which I didn't realize when I signed up for this also entitles me to review a seemingly endless stream of manuscripts from JACC, heart failure, and clinical electrophysiology. I feel they can use my services whenever they really need it.
We just wonder when you're going to get some statistical experience.
Anyway, the reason that I'm wanted to do this is because the presentation here is probably somewhat specific to my experience, and some other statisticians may or may not have the same ideas as I do, but mine are basically based on the study sections I've seen, the manuscripts I've seen, I've reviewed, and for the last quite a number of years, it's heavily oriented towards reviews and the manuscripts in heart and vascular. So, with all due respects to the cardiologists in the room, a lot of the issues here I've seen in cardiology and heart and vascular manuscripts. Okay, so I wanted to give you kind of an outline of what I'm going to talk about here. And like I say, I'm not sure I'm going to be able to get through all of these, but we'll see how it goes. Statistical significance, sample size and power analysis, that's one I'm kind of a major one. I'll talk about correlated data, nonlinearity, about non-parametric statistics and their use, correlation versus equality, and I want to end up with talking about communication between investigators and statisticians. So I've taken some examples here right out of manuscripts I've reviewed. So and I took out the actual variables, the outcomes that they were looking at, and just put in numbers or not numbers, but notation for them. That's basically, I wanted to change the names to protect the guilty. So in statistical notation, Greek letters usually indicate a population parameter like mu, population mean. Roman letters indicate a sample statistic. And then I'm using capital Roman letters for treatment groups of interest, and then lowercase x's for covariance predictors, risk factors, and so on. Okay. This is probably the most important slide of the whole presentation, so if you don't remember anything else, remember this slide. If you have, I guess you will have access to the slides, so if you want to just print this one out and post it on your bulletin board or in front of you, this is it. So if you think of statistics as a measurement of certainty, you really have, in just a couple words, what statisticians do, what their main goal in life, what their purpose in life is. Okay. So as you think of doing a research study, there's different sources of variation in your study. There would be treatment variation. So like if you want to look at like 2 treatment groups or more, there's demographic variation or clinical variables, comorbidities that vary from patient to patient. There's time dependency. Variation, like if you had daytime blood pressure versus nighttime blood pressure, you were looking at blood pressure as an outcome, that would be something important. Then there's just individual patient variation. Then there's cluster variation. So like if you get data from different hospitals or different healthcare systems, that's a source of variability. Then there's measurement error. Measurement error is totally ignored in medical research. And I think probably I'm not going to even talk about this now because you get me started and but I think I probably will in the future sometime do a session on on that, on measurement error, and developing like surveys, and, instruments together, patient-related outcome data. And then missing data, and again, that's another one I'm not going to really talk about here. We've talked about that before, and I may have another one on that. Is, can you ignore missing mechanism, or is it non-ignorable? And then finally, and this is the one that is sort of the earmark of statisticians everywhere, is what we call random sampling variability. And so I wanted to give you just kind of a quick course in introductory statistics here in about 4 or 5 slides. And I can see that probably a lot of people already know this that are here, but let me do it anyway, just to make sure that you understand what statistics is all about. So the idea is that when you do research, that you draw a sample, it can be random or non-random, from some population that you're interested in. And so the basic question is your sample representative of the population? So you're going to use that sample to estimate population parameters. In other words, you're going to use like an estimate of the mean or a correlation or an odds ratio that you think is true of the population. From at least one perspective in statistics, the statistical analysis then is then based on the idea of, well, what if you could draw a large number of samples from the population? And so, of course, you can't do that because you usually don't have the money to draw a large number of samples. You only get one chance at it. But if we could draw a whole bunch of hypothetical samples, what we would get is if we look at a population here of blood pressures, diastolic blood pressures. Let's say that this is my population that I'm interested in. And so what I'm going to do is I'm going to randomly sample 5 values from this population. And this is my sample. So the question is this sample that I got representative of the population as a whole? So what I would do then, it turns out that the mean of this population is 76. So how close does the mean of my sample come to the population mean? And then if I were able to draw a large number of samples and calculate their mean, then I would get what we call a sampling distribution. And so here is my particular sample. And then the question is my sample representative of the population? And so how, in a sense, accurate is my mean in relationship to the population? And you can see that you get a fair amount of variability here, that you might get a sample that's not representative of the population. So, for example, you would, maybe get a sample here that has a mean of 84. Well, that would be quite a distance from the population. In other words, you wouldn't have a very good estimate of the true population mean. So when we do statistical analysis, that's basically what we're doing, is that we're looking at, we're using sample to estimate a population parameter that we're interested in, and what we want to know is how good is that estimate. So when we do then statistical hypothesis testing based on our sample, what we're doing is looking at, as I mentioned, how well our sample represents our population. So in statistical terms, statisticians have 2 hypotheses that they're interested in: the null hypothesis and the alternative hypothesis. The null hypothesis is basically that the population means, say, you get two different populations here. You want to test whether their means are the same. So that's the null hypothesis. We're going to assume that the means are not different in this case. We could use any statistic here, correlation or whatever. The alternative hypothesis is that they are different. And so what statistics does is that it analyzes this in terms of sampling variability. In other words, based on the fact that we have sampling error, sampling variability, what is the probability that our test statistic is going to show us whether we have a true difference or not. So our test statistic is basically some difference here in sample statistics, like these are means, and then we divide that by some measure of sampling error or standard error. And the test statistic has a theoretical distribution like the normal distribution or the t-distribution. And so basically what statistician starts out doing is we assume that the null hypothesis is true. And then based on that, the p-value that we get in our statistical test is the probability of obtaining a value of t or larger just by random sampling variability. That's what a statistical test is all about, what a p-value is all about. Okay. And so the concept here of assuming the null hypothesis is true, is key, because we know everything about the null hypothesis because we have a sampling distribution here. We can describe the sampling distribution really well. We know nothing about the alternative distribution. Okay. So just to do it graphically here, if we have a sampling distribution here and we get a p-value of 0.05, what does that mean? Well, that means that if we get a statistic, like a t-statistic, that is greater than or equal to 2 or less than or equal to -2, then we can say that we have statistical significance, because there's a small, or at least we say there's a small probability that difference that we got between our sample statistics is due to random sampling error. Anybody who's had a basic statistics course probably knows all that, but I just want to remind you of that. Okay. So then, for example, like the null hypothesis of for any sample statistics, like if we are looking at correlations, then our null hypothesis is the correlation equals 0. If we're looking at difference in means, if the difference is 0. When we do regression, the null hypothesis is that the regression coefficient is 0. If you're doing logistic regression or survival, you calculate an odds ratio, hazard ratio, then the null hypothesis is that those are equal to 1. Ratios. If you have a ratio of 1, that means that the numerator and denominator are the same. Okay. So the first topic here of how this is misused. Okay. So when we talk about statistical significance, how small of a p-value is statistically significant? Well, in medical research, I think everybody knows that p less than 0.05 is kind of what we call the industry standard. Okay? But why don't you use 0.01 or 0.06 or 0.1? The point here is that statistical significance, the cutoff value for the p-value is arbitrary. Now, the 0.05 has a long history. I think it's due to one of the pillars of statistical theory, R.A. Fisher, who made a comment that unfortunately probably got set in stone when it really wasn't meant to be set in stone. I don't want to get too far afield here, but my thought is that setting the statistical significance level, just doing that outright at 0.05 for everything, probably should depend on what it is that you're looking at. Okay? But like I said, I can't get too far afield here. Okay. This is a statement that I think everybody probably knows. Every clinician I know would probably agree with this. Anybody here who doesn't agree with it? Okay. That you can find statistical significance when the actual difference or the correlation or whatever it is not really meaningful. In other words, it doesn't have any clinical significance. Okay. I don't think I've ever met anyone who would disagree with that statement. The problem then is when you actually go to write up the results why do we abandon that idea? Okay. So anyway, clinical significance, what we mean by that, just an example here. So for example, blood pressure. We would know that a high blood pressure versus a low blood pressure has some adverse health consequences. So that would be a meaningful difference. When we did the COURAGE trial and looked at the outcome of some of the scales of the Seattle Angina questionnaire, we came up with, or I didn't, but there were some cutoffs that if you had a change in some of the different domains of here, that would be clinically meaningful. So like if you had a change in physical limitation score that was greater than or equal to 20, that would be clinically meaningful. Now, these aren't arbitrary. They were derived by clinicians, by cardiologists who looked at the items that make up this and determined, based on the scales and what they meant, what would be a meaningful change. So that's what we mean by clinically significant. So here's and I pulled this out of one of the papers that I reviewed recently, but it's so standard that you could plug this into almost any research paper, research manuscript. And so as you look at this, there's a number of things here that tells you sort of what they're going to do, although a lot of times you're not really sure exactly what they're going to do. So they say here that with the continuous variables, they compared them using student-centered t-test or the Mann-Whitney u-test based on the distribution. So right away we know, well, okay, they're aware that some distributions may not be normally distributed, so they're going to use a non-parametric test. And then they use multivariable logistic regression here for predicting their outcome, why. They use the Kaplan-Meier survival curves. But the one that I have bolded here, a p-value less than 0.05 was considered statistically significant. That appears in almost every statistical methods paragraph or section that you see. I don't know that I've ever seen anyone put in one that's a different 0.05. So, what are the misuses here? Okay, the first one is the difference between A and B was highly significant. Okay, and then they give some p-value that's really, really small. There's no such thing as highly significant when it comes to hypothesis testing.
I use it all the time.
We're all at fault.
So now if you said the difference between A and B was statistically significant, that would be okay. But high and low doesn't have any meaning when it comes to this is so what this means is that there's 1 in 10,000, a chance of 1 in 10,000 that you would get the results just by sampling distribution, by sampling error. Well, what if you had set your p-value at 1 in 100,000? This would not be statistically significant. Now you say, well, nobody's going to set p-value that low. Well, I don't know, maybe in some situations maybe you should, but the point is that that's an arbitrary, 0.05 was an arbitrary cutoff. So compared to this, yes, it's like 5 chances out of 100 versus 1 out of 10,000, but irrelevant as far as the distance is concerned between the two. Okay. Here's another one. There was a trend towards significance, and your p-value just misses the spot. Okay. There's no such thing as a trend in p-values. It's either significant or it's not. Okay. Now, why do they put this in here? Because this is a value statement. This is saying that my difference here is important. And in fact, I've done analyses where you can get a really small p-value, but the difference is so small it's not worth really talking about. So, and the same thing with trend. That's saying that, well, okay, we just missed significance, so it still is kind of important. Well, if you set it at a 0.05, then not. Then another misuse here of statistical significance is that they do many tests with no correction for type 1 error rate. I'm not going to get into that, but so and actually this is in an article that I looked at reviewed a few days ago. They must have done, I don't know, 50 or 60 t-tests on every variable that they've had in their in their data. Well, the problem with that is the more tests you do, you're bound to find significance sooner or later. It's sort of like if we keep going long enough, do enough tests here, enough analyses, eventually we'll find something. So that's another problem that appears in a lot of medical research. And then perhaps the most important one here of all of these is that to make the statement that there was no difference between A and B and give a p-value that's greater than your cutoff value. You can't say that. Okay? You can't say that there was no non-significance doesn't mean that there wasn't any difference. You don't know. Because maybe there was no difference because there actually is no difference in the population, or maybe there was no difference because you didn't have enough subjects, patients, to detect that difference. So this is a statement that an untrue statement. You can't make that that statement. Again, if you say there was no statistically significant difference, that would be okay. But just to say there's no difference, false statement. A misuse on p-values. Okay, sample size and power analysis. So when you do a study and calculate the sample size you need for the study, typically, say the error rate is usually set at 0.05, and the beta error rate is usually 10 to 20% error. So that means if the beta error rate is that, the power is usually calculated for 80 or 90%, or the sample size is calculated for power at 80 or 90%. So to do this, what you need to do that is an effect size. That is, how big of a difference or how big of a odds ratio do you want to be able to detect, and then some estimate of the variability in your data. You can get these numbers from maybe you did a pilot study, so you have some data that you can use as an estimate. You can use published results to come up with these estimates. Or maybe you have the SAC, the Seattle Angina Questionnaire. Maybe there's a difference that's clinically significant that you want to be able to detect. If you have absolutely no idea, and I've done quite a few of those where the investigator has no idea, then we can do some reasonable guessing. So what I would give you here, if you have no idea, is kind of based on what kind of numbers you get from your variable, kind of a range of variabilities like standard deviations and differences and how many subjects you would need. And usually, though, sample size is not determined necessarily by how many you actually need. It's often determined by how many you can afford. Okay. So from a statistician's point of view, that's kind of always a trade-off is how many you would need to detect the difference you want, and how many you actually can't get, or if you're enrolling patients in a study, how much time do you have to enroll the patients. So sample size is usually calculated for the primary outcome if you have multiple outcomes or several different hypotheses, and sometimes we would calculate power for all of those, and then we kind of pick the one that needed the biggest sample size and go with that. Okay, what's the problem here? Well, the biggest problem is that people do a post-hoc calculation of sample size needed to achieve statistical significance based on their results. So in other words, what they're doing is saying, well, after I found my results and they weren't significant, if we had only had 23 more patients, our results would have been statistically significant. Okay. Now, people who know me know that there are very few things that I get upset about, or that I pound my fist on the table, or get up on the table and stamp.
You want to see that.
But this is one of them. Okay, you can't do that. Okay, the study is over. You know, it's finished. If you calculate power for a different number of patients, then you're changing the data, so your calculations are going to be all different. And so basically what you're doing here is that you're using power analysis to make statements about your research findings. And you can't do that. That's not the purpose of power analysis and calculating sample size. Now, this is just kind of my Reader's Digest explanation of this. There's a paper that came out probably 15 years ago, and I got a couple copies there if you're interested in that, or I can get you another copy. The one by Honig and Heisey. So they give a much more detailed and theoretical explanation of why that's improper to do. I mean, you can use your results to calculate sample size for another study that you're going to do, but you can't use it to make inferences about your current study.
But in clinical trials we do interim analysis, which is kind of different.
Yes, that's different.
Also, I'm sorry, the sample size is still calculated at the beginning.
Yeah,
no, it may not be.
Yeah.
Sometimes people modify the sample size given the results you get, but that's still different from this.
This is different from that.
It was here they're trying to interpret the study.
Right. Yes, there is a whole thing on doing interim analyses and then adjusting your sample size as you go along. There's a legitimate way of doing that.
And people do it illegitimately.
Right, and people right. But this is using power analysis after you've gotten your results, and they didn't turn out like you wanted to, and say, well, okay, but we would have more subjects, we would have gotten statistical significance. Interestingly enough, and they cite some in the article this was a requirement for journals made this requirement to do non-significant results. Now that was like 15, 20 years ago. And most of them were like basic science. There was a few psychology journals. I don't know if they still do that.
They told them to do this?
Yes, they made them do that. Yeah.
It wouldn't be kind of not useful, but interesting to see. I mean, if you don't have a difference, and that's exactly what you said. If you don't have a difference, if you don't have a statistical difference between your samples, your groups, you don't know whether it's because it's a true non-statistic or whether you don't have enough patients.
And you will never know that.
But what you can do is you can look at the 95% confidence interval difference. There are things you can do.
But recalculating how many subjects you needed, you can't do that. Because if you do that, like I say, you're changing the data. So you wouldn't get the same numbers. Now there's a real difficulty in communicating that to investigators. Like I say, I don't know if there are journals that still require that, still do that, but it may be that after this article came out. Okay. And so another thing that is a misuse here is that in research articles I found that when they do their sample size calculation in their methods section, they're basically basing it on a t-test or chi-square. But then when you get to their results section, you find out that, well, they didn't do a t-test or chi-square. They did something more complex. So is their sample size and power analysis calculation correct? Well, maybe they got lucky, but that's not correct. If you need to do the power analysis on whatever statistic it is that you're using.
But do you? Because power is really to help you get the trial started. What you do after the fact is analysis of results. Now, I think the important point there is you should say in advance what you're going to do. Right. Otherwise, you can keep doing things until you get the result you want. Even if it's not multiplicity, you just do some kind of thing. Well, t-testing would be what I want. Maybe I can get it out of regression.
Well, that's true. You can do that. But if you said that you were going to do so you're going to do, say, a mixed effects repeated measures here, then it would be improper to do your power analysis just based on a t-test. I mean, I know what they're doing. What they're doing is they want to take one of these repeated measures, say at the end of at the end of their follow-up study, and just compare those two means. But that's ignoring everything else that happened in between that. Okay, correlated data. So we all know what correlated data is. So you have measurements on the same patient, different measurements on the same patient. Okay, so this is really clear. So here we have patient age and patient blood pressure. Correlated data. These data points come from the same, they're related. Okay. Or if we do repeated measures, that's obvious to everybody. You have observations over a time period here on the same. Those are correlated. But come to the situation where you have something that's not maybe as clear to people. So for example, here we have patients who have a certain number of stents, and then we look at something here like stent fracture. These data between patient 1 and 2, those are uncorrelated because they're independent. These two measurements are not, because they come from the same patient. And for some reason, it seems like investigators can't make the transition from looking at the obvious things like repeated measures to this sort of thing to say that these are correlated. And so what you end up getting is an analysis of stents, treating them as independent observations. They're not. You have to take into account in your analysis the fact that these are correlated.
So these, for example, on patient ID 1002, these will be two different stents, and one that has fractured and one that hasn't fractured. In the same patient.
In the same patient. Why that's so hard to make that leap, I don't. But anyway. Okay, so then we'll do another level of non-independent data here, which may get me in trouble here. So, so the Courage trial was really a multi-level study in that there were hospitals from different healthcare systems. So Canadian hospitals, VA hospitals, and U.S. non-VA hospitals. So here is my diagram of what this looks like. So you have up here what we might call healthcare systems. Then within each healthcare system, you have different hospitals or different sites. And then within each site, then you have the patients who are actually, randomized to the treatment, PCI or medical therapy. So the point here is that by virtue of coming from one site or one healthcare system to another, that these data here are correlated. In other words, the fact that that these are, even though they're randomized, these are not independent groups necessarily. They might be correlated. So What happens is that you then analyze the data as if it came from one big homogeneous pool. So like when you have data from just one institution, then you don't need to worry about that because it's just coming from one institution. But often, especially nowadays, large trials are based on data from even different countries, which actually makes this somewhat even worse. So there's an easy fix for this, actually, or an easy way, fix, I guess, but an easy way to test this. So what we would do in the analysis is patients, of course, are always random. We would treat healthcare systems and sites as random effects and build that into our analysis. So what that does is it then accounts for variability between the healthcare systems or the sites. Because we're typically not interested in comparing healthcare systems or comparing hospitals. We're interested in the overall question about the particular patients here. Stable coronary artery disease patients and whether PI or therapy was better. Now, it's possible that you don't have to worry about that, and we can do statistics to determine whether this correlation is big enough to worry about. So if we can show that this correlation is really small, then we can ignore the multi-level or the hierarchical nature of our study. So in the Courage trial, in the original paper, which I had nothing to do with, I don't think they did this. When we looked at some of the other things, some of the secondary hypotheses, I actually looked at this.
What did you find?
I found that the interclass correlation was less than 0.1, so we could ignore it.
So the random effects by either site or healthcare system is generally ignored. And you've been on that one for years, and maybe what we ought to do is write an editorial that people ought to at least look.
Yes, I think they need to do that. They need to look at it. If we were in education doing educational research, we would have to worry about it, because if you have like students within classrooms, within schools, within districts, the correlation could get quite high. And you would need to then pay attention to that.
Yeah, this is actually a very sensitive issue with the FDA, because the FDA's mandate is to approve drugs in the United States. Many large global trials will have a certain percentage of patients in the United States and a certain percentage elsewhere in the world, like in Europe. And they will always look to see if the results differ. And I've seen several important trials where the results did differ. And trying to make heads and tail after the fact of why they differed, whether it was the patients, healthcare systems, is very difficult. It puts them in a very sticky position to approve a drug where the overall results are positive, but the results are negative, are trending in the wrong direction.
Well, there's one you'll know about well in that regard in particular.
I know.
And you know exactly what I'm going to say. It's Ticagrelor,
Right.
where there was the trend in the opposite direction in the United States. And it was very, very tricky to figure out what to do with it.
Like I say, it's probably 90% of the time we can ignore it, but it does need to be looked at least checked. And so when I review papers at multi-site, I put that in there. You need to either treat these as random effects or at least show that they can ignore it.
You're probably one of the few statistical reviewers that does that. And, I think that better make this problem well known. Because, you're right, Rick. The FDA knows it, but most clinical investigators have no idea.
Yes, there needs to be a culture change. But anyway, okay. Let's see. How am I doing here? Well, let me do one more here. Let me do nonlinearity, and then I'll just skip to the end. When we do linear regression or logistic regression, the assumption is that our covariates, that is, or the predictor variables that we're looking at, are linearly related to the outcome. That's an assumption made. So what happens, though, if the relationships are not linear? Well, if they're not linear, then the regression coefficients you get here are misleading, or they're invalid, or they're just plain wrong. So, for example, and this is just my Googling here, but it did come from an article that I did review. They had this kind of pattern of relationships between X and Y. And you can see that not exactly linear. You have a curvilinear trend here. So of course, we can do a linear, regression. But it turns out that doesn't fit well. That we can fit it better nonlinear. So basically, when you analyze something that actually is nonlinear in a linear way, then you get results leading conclusions. So there are several ways that we can handle nonlinear relationships. We can do polynomial regression. That's the first one. You raise the covariates to different powers. Piecewise polynomial regression, or we can use splines. I like to use fractional polynomial regression. That's kind of easy to do, and tells you fairly quickly whether you have linear or nonlinear relationships. And then kind of a last resort here is we actually fit a nonlinear equation. You don't really see this much in the medical literature. Where you see this is in basic science literature. Because when you actually do a nonlinear equation here, these coefficients have some meaning. Like they're either a point of inflection in your curve, or they're like the baseline or the asymptote. So they actually have some meaning there. So I just wanted to do an example here. So I did an analysis. This is from the hospitalist data on hospital length of stay. And so if we do our just regression here, length of stay is our outcome, and then these are some variables that we think might be associated with length of stay. So if I just do this, and without regard for whether these relationships of these variables with hospital length of stay is linear or not, then that's the assumption that I'm making here when you see this. My perception is that this is probably ignored in most published studies. They just give you the regression coefficients. But it turns out that when I did this, that there's actually a nonlinear relationship between length of stay, hospital occupancy. See that from the plots here, that we really need to investigate whether the relationships are linear or nonlinear to get a model.
Well, let me. When you review a paper where there is some type of regression, do you ask systematically the author to check whether it's linear?
Sometimes.
They don't say
Yeah,
it?
sometimes. All the time, if they have a graph plot, a regression plot in there with scattered, clearly nonlinear.
I mean, that's one good clinical reviewer should pick up as well. I do that all the time.
Yeah.
I've had, because I'm not a statistician, I get pushback. Sometimes I've said, no, you don't understand. You will do this, or your paper is not going forward.
Yeah. So, is your data unnormally distributed, or is it normally distributed? So these are typical things that you see. Paragraphs, statistical methods paragraph. They check the normality of the distribution. If some are non-normal, then they use the non-parametric statistics. And this is my favorite here. Non-normally distributed outcome variables were log transformed. And I don't think I've ever seen a different transformation mentioned. Everybody log transforms their data. Why do they do that? Well, somewhere along the line, I guess in a course or something, they thought, well, if you log transform something, that's what you do. I've always wondered, after you do the log transformation, did that make it any more normal? Well, sometimes it does. So here's I think there were 3,000 PSA values, and these are the original units. You do a log transformation, it comes out really pretty. On the other hand, you do length of stay, it's pretty skewed. If you log transform it, it's still skewed. So, haven't gained anything. So my perception is, although I'm not for sure, but that they log transform data and then they do the analysis, but it's still on skewed data. So
people do that all the time. Misuse cost data a lot.
So yes, cost is another one that's highly skewed. Do a log transformation, it does nothing to make it look normal. So anyway, the comparison here between groups that I often find that when they do their table 1 and they're looking at the outcome and they find out that it's non-normally distributed, they do a non-parametric test. But then they turn around and use the same variable as non-normally distributed in a parametric regression analysis. Okay, so somehow there's not a connection there in what they're doing. And then, are you interested in the mean or the median? These non-parametric tests are rank order tests. In other words, they're testing ranks. They're not testing means or even medians, although there is a test for medians. So it's what particular is the statistic you're interested in. The question that you probably should ask, whether your data is normally distributed or not, are the residuals normally distributed, because that's what's important. You can have normally distributed residuals with non-normal data, but always. So here's an analysis again I did predicting length of stay, a number of different variables. This is bridges data, I think. So I do my model here for length of stay. Remember how length of stay was not very well normally distributed. It's pretty skewed. So if I just give this, then I've probably misled readers because the residuals are not distributed. So I have to do something else, which I don't have time to do. But anyway, that's another
I don't think anybody here understands what a residual is.
A residual is just the difference between your predicted value you got from your model and the observed value. And the assumptions that most statistical tests make, parametric statistics, that those residuals are normally distributed. Okay, let me skip that because I'm out of time. Go to communication. This is another important. Okay, so typical view of the statistician's role in the design of a study is, how many subjects do I need? That's kind of it. But statisticians can be of big help in other aspects of designing your study. So, like categorizing scales, numerical scales, you help clarify the hypotheses, and then how you might format your data for the analysis, as I mentioned in the important slide with some sources of uncertainty. So statisticians can be a big help in designing the study rather than just simply calculating how many patients you need for your study. So communicating with your statistician. So if the investigator has a hypothesis like this, we want to investigate the feasibility, safety, and outcome of endovascular recanalization of needed chronic total occlusions in patients with failed lower extremity bypass graft. Now, as a statistician, I'm probably going to need a little help figuring out what exactly they mean here and what exactly they want to do. But I can do that because I have some idea here, and as we kind of talk through it, I can figure out what their hypotheses are, what their outcome variable is, what they want to do in terms of the questions they make. So if we get that figured out, and then I come back and say, well, okay, if I understand that, then this is the likelihood function we need to maximize. Well, that probably isn't going to help as far as communicating with the clinician or the investigator. So communication is, a two-way street. I need to put this, even though this might actually be what I'm going to do, I need to put it in terms that the investigator can understand. Okay, so let me finish up. One more thing here. Questions you should never ask. So, I collected data on 100 patients. Do you have any idea what to do with it? Okay, I have data I collected, 3 patients in Group A and 7 in Group B. Can you tell me if there's a significant difference between the two? Okay, well, no, let me not get started on that. Because there are a number of articles reviewed where they have a small number of patients in the group and they're doing all kinds of statistical tests. If you have a small number of patients, there's really not much you can say. Then you do my research project for me. Now, to be honest, only residents have asked me this question. But they have asked. And then finally, the question that is probably the statistician's favorite all over the world. Can you find anything? Thank you. I think we're out of time, but
So, when we do a table 1, where we have all kinds of variables that we are comparing between maybe two exposure groups or 2 outcomes, but in table 1 it's mostly 2 outcomes. And do you need to do the Bonferroni correction? Even though you have all your regular variables, so the demographics, and when it's cardiology paper, you have all the stance characteristics and all these kind of things, which is really complicated. And you have then 30 variables, 40 variables that you compare. I've never seen a Bonferroni correction.
No, and that probably wouldn't really help either, because when you have a lot of variables and you do a Bonferroni correction, then it's like you do get a p-value, less than 1 in 100,000, which is difficult. So.
But, Claudia raises a very important point, because the New England Journal has been back and forth on this. For a long time on the covariates, they said no statistical inferences, just give us the data.
Yeah.
And then they changed their mind as it's back in. But generally without correction.
Yeah, good. That makes it.
Well, I think table 1. Okay, well, first of all, if you do a table 1 randomized trial, there are statisticians who said there's no point in doing that. You randomize and there's no point in in comparing those. I'm not sure I entirely agree with that, because there's no such thing as a truly randomized trial. People anyway, you can with rats, but anyway, because people can choose to be in the study, they can choose to drop out or whatever. So it's not, but it's maybe random enough, but it's not truly randomized.
But you can also have imbalance, and the statistical inference testing can give you some idea about the importance of the imbalance. So I might also add that your point about P equals 0.05, can it not be emphasized enough? And the FDA is already there. They will not accept a p-value of 0.05 for a single trial for registration purposes. You either have to have 2 trials of 0.05, or I believe the p-value was 0.001.
As I recall, that's what we did in the Courage trial when we gave the list table. We had the p-value at 0.01, not 0.05, which is maybe not entirely correct or maybe the best, but at least it's.
But you need to define it in advance.
Right, but you need to define that p-value in advance. Not, well, if you're doing a trial, you need to, but
We actually had an interesting discussion, you may remember, with the New England Journal about that and the quality of life in courage. And there was, it was back and forth with them about whether we should try and do some kind of multiplicity testing. Our argument to them, which they ultimately accepted, was that it's impossible. There's just too much going on here for us to realistically do that. But we had written into the original methods in 2001, you know, and the methods paper written several years before, and they were ultimately fine.
Thank you.
Thank you.